Hello everyone, welcome back. So, we are in lecture 2 of week 3. So, let us continue our discussion and we are going through the 3D stress analysis. So, 3D stress analysis. Okay. And in the last class we have also defined the 3D stress field. If I quickly draw, so we have a body of size delta x, delta y and delta z, and the coordinate systems that we have is marked as x, y, z, as you can see on your screen, right. And what are the stress components? Let us quickly draw. So, this is sigma xx, then we have two more components. So, this one is tau xy and this one is tau xz, right. And on this face we have sigma xx, then this is tau xy and this one is tau xz. Similarly, on this face let us use a different color. So, on this face we have sigma yy and there are two more shear stresses. So, this one is tau yx, obviously it is equal to xy, and then this one is tau yz. Similarly, on this surface we have sigma yy and then here we will have tau y x and then this one is tau yz. And the last component, let us mark it here. So, on this surface we will have sigma zz and then two more components. So, this is tau zx and then tau zy, and on this face we will have sigma zz and this one is tau zy and the last one tau zx. So, that is the stress field, and then if we consider plane defined by n, which has three components nx, ny, nz. So, these are the direction cosines. Then on this plane we have the traction T. So, Tx, Ty and Tz that we have evaluated in the last class. What is that quantity? We have the stress field. So, this is sigma xx, tau xy, tau xz, then sigma yy, tau yz, sigma zz, It's a symmetric matrix. For the time being, let us assume that tau x y is equal to tau y x. That we will prove, and the same for the other two components of shear stress. So, this will be multiplied by n x, n y and n z. So, that is what we derived in our last class. So, that is the first equation that we consider today, and the total traction T, that is square root of T x square plus T y square plus T z square. That is equation 2. Then we also obtained sigma n. That is the normal stress acting on the plane defined by this direction cosine, that is the outward normal, and for that sigma n we have obtained. What is that quantity? It is T x, T y, T z times n x, n y, n z. So, that is the expression for sigma n. In fact, if we put the expression of T x, T y, T z from equation 1, we basically get expression say n x square sigma x s plus n y square sigma y y plus n z square sigma z z plus twice n x n y tau x y plus twice n x n z tau x z plus twice n y n z tau y z. But look at this three equations, they are very easy to remember. So, we will prefer these three expressions rather than the one we have right now here. Now, we also discussed that how to find out T n. This is nothing but square root of T square minus sigma n square, right. Okay. So, let us solve a quick problem and see how this helps us to evaluate the stress component acting on a particular plane, right. So, example, what we do? We consider stress field which is 20 minus 4, 3, then 60 minus 5, then 45. I am not writing the unit of stress, it may be MPa or any other unit. Now, what we wish to find out, the stress components is sigma n, tau n and T on a plane which is equally inclined with x, y, z. That means, n x is equal to n y equal to n z. Now, recall we also discussed a property of direction cosine which is n x square plus n y square plus n z square is equal to 1. So, that means, the direction cosine in this is 1 by square root of 3. It is plus minus, for the time being let us consider plus only. So, what we will do? First we find out what is T. T is nothing but we have sigma times n, right. Now, we have the stress field given by this matrix and we also have n x, n y and n z. So, if you use equation 1, and find out this matrix multiplication, what you will get, the components are 10.97, then 29.44 and then 24.83. Okay. So, first part we have found out. Now, from this expression we can figure out what is t. How to do that? That is using equation 2. So, if you do that, you can estimate equation 2 and you will get t is equal to 40.05. Again they are having consistent unit, which I am not writing for the moment. Our next task is to find out sigma n. Sigma n, how we work it out? Using equation 3. So, we have the components of t and we also know n x, n y, n z. So, again if you do that multiplication, so what you will get is sigma n as 37.67. And finally, we can find out tau n. Tau n is nothing but using these two by putting in this expression, which is in our case, let us give it a equation number of 4. So, from 4 we can find out this expression and it is 13.60. See how easily we can find out the stress components acting on a plane which is defined by the direction cosines. Okay. The moment it is given, we can find out the stress component, and then if we keep on changing the orientation of the plane, we can figure out what are the stress component acting on that particular plane. And obviously, our next task will be to find out the plane where shear stress is 0. That we will do as we progress in this course. But for the time being, let us consider a case where we will prove that tau x y is equal to tau y x. So, let us prove this and then we will move forward and find out basically the orientation of the principal plane. So, that let us do it. For that, we need to slightly modify this stress block diagram, that we will do in a minute. So, what we have to do, we will start from say x plane, and the left one is marked on your screen, and then we will consider the variation of this stress as we move along the x axis. Obviously, the dimension of this block is delta x, delta y, delta z. So, if we move along this positive x, we can find out the variation of axial stress or normal stress, we should say, and shear stress, right. So, what will be that component? Let us identify that. So, we have delta x y is the length over which the stress will vary. So, we can write down that variation over x. So, this is the variation. Similarly, if we consider the shear stress, on the left hand side we have say this tau x y. As we move over a length of delta x, then so this will be plus right. And the last component on the x phase, so tau x z, that will also vary over this length. So, we can write down that expression. Okay. So, now x phase is done. So, what we will do, we will go to y phase and then we will repeat it for the z phase also. So, if this is sigma y, here it will be sigma y y times delta sigma yy times, that is the component. And similarly, the other two we can also write down. So, this will be y and then times delta y, right. Note that now, because we have to prove tau x y is equal to y x. So, on this face we have y x, that we do not change. Okay. So, for the other components, so let us complete that exercise. So, here it will be tau y z plus delta tau y z. Okay. The last phase, that is the z phase, let us complete. So, this will be sigma z z plus increment of sigma z z over z axis times delta z, right. Then this component, let us write it here. So, we will have tau z x plus variation of tau z x over z times delta z, right. Okay. So, for this one, the component is tau z y plus variation of tau z y over z axis times delta z. Okay. So, now we have the complete stress field where we have considered the variation also. Now, let us mark the sides. So, this is delta x, so this is delta z, and this one is delta y, right. Okay. So, now what we can do, we can again apply the moment equilibrium. So, if we consider moment about z axis with anticlockwise positive, so sum all the components and equate it to 0. Obviously, the question is what are the components that will cause a moment about z. So, let us mark it and then we will see. So, this one is obviously the component that will contribute. So, does sigma x x on the left face. Then obviously, sigma y y. So, this one will contribute. So, does the one at the bottom sigma y y. Obviously, tau x y, this one will also cause a moment about z axis, and then tau y x. So, this component, okay, tau y x. The last one you can identify. So, tau z y. So, you have z y here and tau z y there. So, this will also cause a moment about z axis, and then we have tau z x and this one. So, these are the stress components that will contribute to m z, right. So, we have identified, obviously, we have to find out the moment caused by each of them, and then we will solve this equilibrium problem. So, let us consider the first one, sigma x x. So, what we have, sigma x x, it is acting over a plane defined by delta y and delta z, right. So, that is the total force. Then we have to find out the lever arm. It is acting at the mid height of this sigma, delta y. So, the lever arm is delta y by 2. Then we have sigma xx plus its variation and again it is acting over a plane of delta y delta z and the lever arm is again the same. So, this is delta y by 2. The only difference is you can see this negative sign because it is acting in the opposite direction. Then plus we have tau xy plus its variation over x axis then we have to identify the area over which it is acting. So, it is acting over the area defined by delta y delta z. So, this is delta y delta z and what is the lever arm? This is delta x, right. So, we have to multiply this with delta x. Okay. So, then we have tau yx, then its variation. So, plus that is the component here. So, it is acting over phase defined by delta x and delta z. So, delta x times delta z and then what is the lever arm? Lever arm is delta y. Okay. Fine. Then we have sigma yy. So, this sigma yy, it is causing a negative moment. So, we have minus sigma yy times the area which is delta x times delta z multiplied by the lever arm which is delta x by 2. Then plus sigma yy here plus its variation. So, delta y times its variation over y axis. So, we have y here times delta y. Okay. This multiplied by delta x delta z times the lever arm which is delta x by 2. Then minus tau zy. So, we can identify this here tau zy actually here times we have the plane defined by delta x delta y times the lever arm is delta x by 2. Plus tau z y plus its variation over z axis. So, tau z y z times delta z times the area delta x delta y times we have delta x by 2 as the lever arm. Then we are almost done. So, we have tau z x, then it is acting over the area delta x times delta y and the lever arm is delta y by 2, right. Tau z x it is here plus tau z x plus its variation. So, we have tau z x divided by z times delta z and the lever arm delta x delta y times delta y by 2. So, this will be equal to 0. So, these are all the moment components along z axis, right. Now, obviously, you can see some of the components will be cancelled, as you can see here, this one and this one, and then we will get the simplified form. So, let us quickly write down the simplified form here. So, we will have minus, you can see this will get cancelled. So, we will be left with this component. So, minus variation of sigma xx over x axis times the lever arm. So, we have delta x, delta y, delta z times delta y by 2. Now, what is this quantity? This is delta v. So, we can modify this. So, let us modify. So, delta v times delta y by 2, that is the lever arm. Okay. Then here we will have plus tau xy and then delta v. Then we have xy here plus this component. So, that is plus delta v times we have delta x plus, again here you can see this will get cancelled. So, we will have variation of sigma yy over y, then delta v times delta x by 2, then minus tau yx times delta v, then obviously minus variation of tau yx over y axis. So, we will get delta v times delta y. Then we have minus variation of tau zy times delta v times the lever arm delta x by 2. And the last component plus variation of tau zx divided by z times delta v times the lever arm delta y by 2. Right. So, what we can cancel is delta v, because that is the common term. So, we can cancel it, and then if you look at, if in limiting sense limit delta x, delta y, delta z tends to 0, all these components, say for example, this one will be 0, except we will be left with this quantity and this one. So, that means we have tau xy minus tau yx is equal to 0. That is, tau xy is equal to tau yx. So, you can see for the 3D, if we consider the variation of stress along x, y, z, then also we can prove that cross shears are equal. Now, we have done it for tau xy and yx. Similarly, we can also do it for xz is equal to tau zx, and then tau yz is equal to tau zy. These two I leave it as an exercise for you. So, what you have to do? You have to find out the moment about x and y axis, sum them up and use a sign convention. Here anti-clockwise is positive. So, sum all the moments about x and y axis equal to 0, and you can easily prove the remaining two. That I leave it as an exercise for you. Otherwise, it completes the proof, and we can now safely use that cross shears are equal in a 3D stress field. So, 3D stress field is symmetric, right. So, with that, let us stop here. So, what we will do next is we will find out a plane along which the shear stress is 0, and that will be the principal plane. So, that we will do in the next class. Thank you very much.